In note 6.4, examples 3 and 4, we are going to repeat the analysis that we did for sine for cosine. So we're going to learn how to build the graph of f of x equals cosine x. In the top right corner of the notes, I have drawn up here the first quadrant of the unit circle. I put the angles in 0, pi over 6, pi over 4, pi over 3, pi over 2, and then the points on the unit circle, the order pairs. So when we're looking at cosine, we're going to be looking at the x values on the unit circle for each of these angles. So let's begin finding the values for cosine x or cosine theta. I'm going to start with 0. When I have an angle of 0, we're going to be at this point on the unit circle. The x coordinate here is 1, so that means that cosine of 0 is 1. Next, we're going to go to pi over 6. So when we're at pi over 6, we're focused on this point. The x coordinate is rad 3 over 2. So let's fill that in. So at an angle of pi over 6, the x coordinate is rad 3 over 2, which is cosine of x, and that is about 0.87 if you got a decimal approximation. We're going to move to the next point on the unit circle. That angle is pi over 4 right here. The x coordinate of pi over 4 is rad 2 over 2. So let's fill that in. So we've got pi over 4. Cosine of pi over 4 is rad 2 over 2, and that's approximately 0.7. The next point on the unit circle is an angle of pi over 3. The x coordinate is 1/2. So cosine of pi over 3 is 1/2. Next point that we're going to do is pi over 2. So that's right here at the top of the unit circle. The x coordinate here is 0. So cosine of pi over 2 is 0. We're going to keep going into the second quadrant. In the second quadrant, x values are negative, so cosine is going to be negative. So the next point we're going to look at is 2 pi over 3. 2 pi over 3 has the same reference angle as pi over 3, so the cosine, the magnitude of cosine is going to be 1/2, but it's going to be negative because we're in quadrant 2. So we're going to do angle of 2 pi over 3. Cosine of 2 pi over 3 is negative 1/2. Next point we're going to take, we're going to keep going around the unit circle. So we're going to be at 3 pi over 4. 3 pi over 4, the magnitude of cosine is rad 2 over 2, but we're in the second quadrant, so that's going to be negative. So we're going to have 3 pi over 4 negative rad 2 over 2, which is about negative 0.7. The next value that we're going to do is, let's see, next one that I would do is, well, I guess we can jump ahead to pi. So when we're at pi, cosine of pi is going to be negative 1. And then we can do 3 pi over 2, the bottom of the unit circle. That will have an x coordinate of 0. And I'll add one cell on here. We'll have cosine of 2 pi. If we go all the way back around, that's going to be at 1. So now we're going to go ahead and plot these values. Just like on the previous graph, the x values are angles, and this scale is counting by pi over 12. So if you remember from the previous graph, this line here is pi over 12. Next one is 2 pi over 12, which is pi over 6. 3 pi over 12, which simplifies to pi over 4. 4 pi over 12, which simplifies to pi over 3. 5 pi over 12 is not relevant for the unit circle. Next one would be 6 pi over 12, simplifies to pi over 2. 7 pi over 12, not relevant for us. 8 pi over 12 simplifies to 2 pi over 3. 9 pi over 12 simplifies to 3 pi over 4. And then we're going to jump ahead, 9 pi, 10 pi, 11 pi, 12 pi over 12, which will be pi. And then we're going to keep jumping by pi over 2, which is six lines. So we'll have 3 pi over 2 and then 2 pi. Those are going to be our x values. So let's go ahead and plot these points. So we've got when the angle is 0, cosine is 1. And when the angle is pi over 6, cosine is 0.87. This is about there. Cosine pi over 4 is 0.7. Remember the x scale, the y scale is every line is 1/4, so 2 lines is going to be a half. So we've got pi over 3, 1/2. So go up 2 lines. pi over 2 is 0. 2 pi over 3 is negative 1/2. Oops, I put that in the wrong place. So let me put up one. 2 pi over 3 is negative 1/2. 3 pi over 4 is negative 0.7. So about here. And 3 pi over 2, pi is negative 1. And then now we don't need so many points. 3 pi over 2 is 0. And 2 pi is 1. 1, 2, 3, 4. And now we can connect these with a nice smooth curve. Remember, don't make them pointy curves like in an absolute value graph. They are smooth, rounded curves. Draw arrows at the end because the graph continues on forever in this periodic fashion. If we go back to negative pi over 2, that will be at 0. So I'll put that point on there as well. And then an arrow going down to show that it repeats. So this is our parent function for cosine. And we're going to do the analysis for cosine. Just like with sine, we're going to show 5 key points per cycle. The key points, again, will occur every quarter period. What's the period for this? So I will show you. The period is what it takes to do one full cycle. So if we start at a maximum, we have to repeat until we get back to a maximum, having one upward cycle and one downward portion. So that is a full period. And then we will have 5 key points in that period. So we'll get a maximum value. So this is a maximum. We're going to get the minimum, and we're going to get the points where the graph crosses the axis of oscillation, which is its midline, and then back to this other maximum. So that'll be 5 key points in one cycle. All right, so let's do the analysis. What's the domain? The domain is all x values. This function is continuous. We don't have any asymptotes or any reason that we can't put in any input for x. So the domain is going to be all real numbers. So I will put that in, negative infinity to infinity. The range is going to be all y values. This periodic function is bounded between negative 1 and 1 inclusive, so that is our range. The amplitude. The amplitude is the distance from the midline, so this is the midline here, to a maximum. So that would be from 0 to 1, so 1 unit, or half the distance, or the distance from the midline to a minimum. Distance is going to be positive, 1, or half the distance from the minimum to the maximum. So negative 1 to 1 is 2 units, divided by 2 is 1. And we're going to talk more about the formal definition of amplitude in one of the next examples. So for now, the amplitude here is 1. And if we want to change the amplitude, we would perform some sort of vertical dilation, stretch or shrink. The period is how long does it take along the x-axis to complete one full cycle, and that is 2 pi. And if we want to change the period, then we would perform a horizontal dilation. Okay, intercepts. The y-intercept, I circled it already because it happens to be a key point for this cycle. And the y-intercept as an ordered pair is the point 0, 0, 1. X-intercepts. Just like when we did sine, we're going to try to write a general expression. The idea is we're going to write a few points and then figure out how we can write an expression for all of them. So x-intercepts, let's see, we've got one here. So we've got one at pi over 2, 0. And then the next one we have, I'll circle it in blue, is at 3 pi over 2, 0. To get from one x-intercept to the next, we're adding pi. So the next x-intercept, even though we didn't graph it, would be adding pi. So we could add another pi, which would be 2 pi over 2. So that would be 5 pi over 2, 0, etc. We could also subtract pi. So we could have negative pi over 2, 0 as another x-intercept, which we actually do have on our graph. That's here. So a general expression, the way to do that is you can pick one value. So I'm going to pick pi over 2. And to that, we need to add a multiple of pi. So it's going to be plus pi n. The y-coordinate is always 0. And then we need to specify that n is an integer. Another way to write that you can say is n is an element of z. Z stands for the set of integers, just like r stands for the set of real numbers. Okay, maximum values. So we've got actually two maximum values shown. We've got the y-intercept and this point at 2 pi 1. So I'm going to list a couple of maxima values. So I've got 0, 0, 1, and then we have 2 pi 1. So to get from one to the next, we add 2 pi. So if I wanted to get another one, I could add another 2 pi, which would be 4 pi 1. So to write the general expression, I pick one value. I'll pick 0 plus the multiple of 2 pi, which will be 2 pi n, comma 1. And normally we wouldn't write 0 plus 2 pi n. We just write 2 pi n, comma 1. And then we have to say n is an integer. Minimum values. Okay, so I will circle a minimum here, which is at pi negative 1. So let me write that down. I have to scroll up. So pi negative 1. To get to the next minimum, I have to add a full period, which is 2 pi. So that'll be 3 pi negative 1. And I can continue on. I could add another 2 pi, 5 pi negative 1. So to get a general expression, I'll pick one value, pi, and add a multiple of a full period. So 2 pi n, and the y value is negative 1, where n is an integer. Okay, lastly, we want to see, is the graph of y equals cosine x odd or even, or perhaps neither? So for that, we're going to look back up at the graph. So if a function is odd, as in the case of y equals sine x, it had origin symmetry. If it's even, then it has y-axis symmetry. So here's the y-axis, and if we look at the graph of cosine x, we can see that it is a reflection of itself over the y-axis. So the graph of cosine x is even, and that's because it has y-axis symmetry. I want to explain this a little bit more. So when I say n, this symbol is epsilon. That means an element of. And z, it's actually a z with a double back. So more like this. That means the set of all integers. And I also noticed that I forgot to plot 1 point on cosine x. So let me put that in. I forgot to plot this pi over 4.7. So let's put that into the graph. Pi over 4.7 would be about here. So our graph would go about like that.